Okay, let's get started. So we want here to draw a little siding station. So I take the track symbol here. We draw now like in a simple painting program. All the tracks I want. Let me do like this. And when we draw here, we get a switch. Then we want to switch here as well. Now I don't particularly like the names here, so I will just call this one 1 and I call this one 2. Okay. By double clicking on a name, I can just change to a different one. Okay, now let's put some joints. So I take one here, maybe I put it there, and I need to invent a name for it, so why don't I call it D1, for example. And then the second one here, D2, put one here, D3, and then we want one here, D4, put one again here, D5, and now I want a joint here as well. That was the last one. Okay, let me put some signals here. I want some entrance signal, maybe here. Would be nice, and I call it S1 because it's a joint D1. And then an entrance here, I right click to change direction, S6. By pressing space, I get a new one of the same type. This one should be an exit signal. So let's call it S3. And this one is also an exit signal, S4. Here is S2. This is S5. Oops. Oh, okay. I couldn't do this. I by accident wrote S4 and there was already such a signal, so I wasn't allowed. Okay, you can adjust if you like the labels here a bit if they are too close or something. Okay, now let's put some track circuits here. So I pick one and here let's call them T1. And here let's call them T2. T3. T4. T5. And T6. Maybe I move this a bit closer like this. Okay, if you hover over one of the names, you can see what the names are for. Like here, it will highlight the signal and where it's placed, like this. Now I want also to add a name for this, so it's a location object. It doesn't mean a lot, but at least I can put in a name. This can also be configured. So for some customers, for example, they have been using this for different controllers. So maybe they have an interlocking with 5 controllers, and then they can put all those controllers out there where they belong. Then we take a direction. Maybe I should call this bit generic name east, and then the other direction, let's call it west. Okay. Move this around a bit. Okay. So you see, I configure this station as in a painting program. Normally there are also some other data like timer values and stuff that cannot be graphically represented in a good way, and they can be entered as tables instead, if you like. Okay, now we have everything we need for this mockup project. There are actually some other kinds of signals I can choose. I can actually change a type to a shunting signal, but here for this purpose I choose to work with only main signals. When done, we can press this button. It starts a computation using all the generic signaling principles that are put into the packages, using also the configuration data that we just entered here by drawing on the canvas. And using these input data together, it can compute the logic for a signaling system for this station. So this is what I do by pressing this one. It computes now the design. It also computes which test cases you need to do for this interlocking, and it computes also safety requirements you need to prove by formal verification. Here's a simulated window opening. I prefer to have two screens, so I have this window on one screen and this one on another screen, because there is lots of useful information in the simulated window. Now I put the other window behind this screen because you can only see one. So let's look at this first. You can see here that the signals they are now all red. You can also see that the points here on the switches are actually straight. So I can try to use this. If I right click here on the signal, you see a lot of commands that could be sent from the office system. So I now simulate that the office system send a command, and I can choose here. I can request the route to be locked. I can cancel the request that has been stored by the interlocking. I can release a route that has already been locked, or I do the same for the other route here. I can also look at various other stuff sorry, not look at, I can set parameters for the testing. GTS means generic test specification. And then I can also run a train. So let's first lock a route here. And we can also request the route to be locked here. I simulated here now two simultaneous routes, and I can also click on tracks to actually occupy them like this. So I can click on the track or on the label of the track. So now we can simulate that the train is approaching. When I click here, the train will occupy this track, and you can see that the signal turns to red here while this is still green. I can request a new route, by the way, exit here. And let me also request an exit route here. So you can see here this requested gray route. It cannot lock because there is a conflicting route. And this is where I also have this request cancellation, so I can remove the request. But now I want the request, so I let it be there. Okay, if you look here at the occupation, we now pretend that the train reached this track. So I remove this. You can now see that this switch is moving. The flashing little arrow. The switch locked. Okay, sorry, I still have an occupancy here. If I remove that one, we can see that the exit route locks. And now it says green, expect green here. Okay, so let's take a train in at the station here. Occupying there, next occupying here. Now you can see that the switch here moves and the route locks. And now the train can continue. So we can actually here also click run train on route, and it will automatically spend 2 seconds per track and leave the station. This is a kind of what I call ad hoc testing. You can try whatever you like, or you can also use it for exploratory testing and things like this. But it's also useful to know that you can use scripted tests. So, for example, here, the simulator, if you open it up, it has some predefined test cases. And again, these are not built into the tool itself. It's part of the packages. So there is a testing package that defines that for each route, you're supposed to try 3 different things. One is this. If you click on it, it explains this is to test that routes are released correctly after traversal of the train. And there are three different ones. This is to test that parallel non-conflicting routes are available when a given route is locked. This one you can open up here to see that this test is run for all the routes. And if you start here, it will run all the tests, and it doesn't run them in real time. It runs them as quickly as it can. So it simply advances time very quickly. And you can see here that everything became green. If there is an error somewhere, it will become red instead here. I will show you a bit of this in the end in the generic application demonstration. Okay, let me also do some formal verification. We have a number of requirements here, also built into the packages, things we are supposed to prove. So let's run them. You see, it was fairly quick actually. 310 requirements proved in 0.39 seconds. We use our model checker PSL inside iLock, and also when you develop something knowing that it will be proven correct using formal verification, then you take care during development not to take any, not to cheat or to make it, to actually follow up all the time that the safety requirements can be proven. So you fix the design rather than spending a lot of time in formal verification. That's why we think it's very important to have formal verification as a built-in tool into the development environment. Okay, now we have tested, we have formally verified, and it remains only to generate the code. So let's do that. I just press OK. In this project, we generate code, C code. This has now been generated, all these folders with different stuff. It can be C code like here, or it can be any language. In fact, the generation of, so we build in this tool a mathematical model of the system, and then the generation of code is more or less only rendering the code in the given syntax of the language. So we can do C, but we can also do many other different languages. Okay, so we have now tested, verified, and run code generation. And it's time to certify that this generated code is correct. So let me show you this. We already generated code. We also need to take the model from iLock, and we need to take the safety requirements. So we can actually dump those. Here, you can dump the model, generate HLL code model. So here is now a mathematical representation of the system to be proven equivalent with the C code. Then we generate also the certification data. So I said it's generic, but that's only the safety requirements. The other stuff, all the configuration and so on, is specific. So here is all the stuff generated here. Let me see. This is the generic stuff. The rest is for this specific application. Okay, now to run Proof Certifier, it's not a Windows application, it's actually a Linux application. So to make it a bit easier for everyone who uses Windows at their desktop, we have a cloud-based service, which I will use for this demonstration. So we need to send the generated C code, the certification files, and the HLL code. So first, I need to zip those by creating an archive, zip folder like this. And then I need to send them. So let me copy the path here, and I go to the site cloud.prove.com. And here we have different tools, but now we use the Proof Certifier for Trident Demonstrator. We need now to choose the file. Take this, the zipped one I created, and then we run certification. So you can see here some old ones completed, and then there is one that's scheduled. So it means that when the server is available, it will start this job, it will do it, and it will email me. I have an account here, so I will get an email when the run is done. The job has finished, and we can see the run here. PSL has proven everything, all the requirements. And the log is here, and you can see in the end that everything was okay. Some requirements has been proved, and everything is okay. You also get an email with this, and you can download the log and everything.